I write a compiler for a simple imperative programming language called Elna, designed after Oberon. The compiler is self-hosted and written in itself. It isn't finished yet, and in the compiler itself I can use only the features that are already implemented. And today I will be looking into the call expressions and call statements into the code generation for the call statements, because they need some improvements. There will be code improvements, and we also need to extend them because the current function calls can be only called with arguments that are one word long. So more complex structures like records or arrays cannot be passed to them, but I do not know how much I will be able to achieve today. So we will switch to the function elna_tac call. And here we have the code that produces the 3-address code for a function call. So it basically supports at most 7 arguments, I think. And we just go through all the arguments and generate a temporary variable, $sign AR, and then the argument number. And then I assign the argument values to some variable, to some structure, but I work with it with a pointer to it, and I adjust the pointer by 4 bytes and send the next value. So we need to replace this code with an actual record. And since it assigns a pseudo to it, I think that this type is actually an operand. So if I split my screen and go to elna_tac operand, then I have 3 fields here, and one of them is this kind field, which is assigned here. And here I allocate memory for it, and memory for it is argument count multiplied by 12, and we save this array in this list structure for the TIC. So it is actually an array, but a dynamic array of operands, which actually makes sense, I think. So let us replace this 12 with the size of one arity operand, and let us try to compile it. I think actually that I opened the file in the wrong editor. Yes, that looks better. arity call was it, and we replace it, and now we try to compile it. So we allocated an array, and arguments operand is actually a pointer to the first array in this to the first element in this array or list. So let us assign it a proper type. We say that it is a pointer to arity operand, and now instead arguments operand, it isn't changed anywhere else. Now instead of referencing the offsets, we can reference it fields. So we can say that arguments operand kind, arity operand, let us find it here, and the first field is kind, and we say that it is a pseudo variable. Then we can remove this line and test the building again. The second field is the value, and the value is the variable name. Here it is called name buffer, and the length is 4, because these temporary variables AR are 4 bytes long. Including the $sign and the number. So we can say that its length is 4. Then we can remove these assignments. And now, of course, we do not need 3 plus assignments, but we can just add the size of the arity operand type. And with this statement we go to the next element in the list. So this is fixed. The instruction is actually a pointer, so we compare it to nil and not to 0. Another thing is that we do not always need these temporary variables for the arguments. We actually do not need them at all. Previously I needed them because I saved some variables in the hardware registers, but now the hardware register location is completely separated from the 3 address code, and since we do not save we do not use the hardware registers right away, we can just we do not need to assign them to temporary variables so that they do not get overwritten by the called procedure. What would it actually mean? So here I generate a copy instruction for each argument, and what I save here is basically just what we see in this line, so sudo name buffer and for, but I actually just could write argument type, argument value, and argument length here. And as we can see, it already compiles. So we do not need the generation of this instruction. And I do not need to append this instruction to the current instruction lists. So, and current instruction is instruction, so current instruction just remains what it was before. Then we can remove all of this stuff. So we have 3 variables, I think. First instruction, current instruction, and instruction. I probably do not use instruction anymore. And we have call instruction. Call instruction is probably the argument. And we check if the first instruction is nil. If so, then we assign call instruction to it, otherwise we append call instruction to the current instruction. Where is the current instruction set? So here we assign nil to the first instruction, and here we assign the call instruction. And we need to save these instructions because this instruction used for arguments. If arguments are not just variables but some expressions, then we need to calculate the value of this expression and save it somewhere. and I set the instruction to it, or I append instructions to the current instruction and then set current instruction to instruction. Okay, let us first remove this hole. Don't need it anymore. And if I remember correctly, it compiled eventually. So then we do not need this buffer, I think. It isn't used anywhere else. And this comment isn't useful anymore, so we can remove it, and we can remove the variable declaration. Let us see how these call get functions work, because they still work with offsets, and we should probably get rid of it. So we have get name, so the size is 44 bytes, and actually I save the arguments also in the array. And this call size function, it is an AST node, I think. So get name parsed called, and parsed call is actually, we can do it in 2 steps. So we have now the ability to replace this type with the proper type. So how it is actually saved? We save the name pointer and name length, I think, at least. But here I actually save only the name, and then we save an array of arguments. So the kind, 4-byte pointer to variable expression, and then a memory chunk for 7 arguments. Which doesn't look like right if I look at the code. how do I write its name? So I save the name in this parsed expression. Yes, it isn't. I just accept that the name of the procedure is always a variable expression, which is actually fine for now. And this thing is actually not a TIC call. It is a node. It is a node. We do not have any types that have call in their name. So let us move to the node definitions. These are this ELNA3, I think, ELNA3 node. And we have ELNA3 expression. And a call is both. It is a statement and it is an expression. So we just move a bit, and now the statements are defined, declarations, other expressions, conditionals. So these are help types. ELNA3 module declaration, procedure declaration. So let us define a type ELNA3 call. It will be a record, and it will also have the kind field of type ELNA3 kind, and its second field. So let us call this thing again, call get name, and look at the comment. So 4 bytes node for kind, 4 byte pointer to variable expression. Let us call it name because it is actually is the collé the right word? So it is what should be called. And this thing is actually an expression, I think. It should be designator, but I think that we do not have a special type for designator. It is the same thing that that is on the left side of assignment statement, and I just write a word here, so it is a generic placeholder type for now. I probably should define later a special type for the designator, or just write expression there because it is it is a subset of expressions. So we have the callee, and then we have the arguments. Arguments are actually a list of expressions, and we have theoretically 7 of them. I do not really understand why I add 8 in here. And with this 7 are ELNA3 expression, basically pointers to expressions. Not sure if it can be compiled. Yes, it seems to be fine. And I think I actually so call get argument count +1 get argument, but get argument starts with this plus 8 and plus n multiplied by 4. And we do not have anything that uses the second word in the record. But well, just for the compatibility, it seems that we need some field here. We're just going to add dummy field here so that the alignment, so that the offset to the field matches how we handle the memory. And then we try to, and I actually think that it is for 8 arguments, because 8 arguments need 32 bytes of storage. Then we have the name. This is 36 and kind 40, and these dummy bytes, so it should be actually 8. And then we can replace this call size with the size of this LNA3 call type. Call size. It is used, for example, in the parser, because if it is a statement. That's right, if it is a statement, then the second element will be statements are a list, and if it is a statement, then it contains a possible reference to the next element in the list. So basically we just say that next is words, so it's not a dummy argument. But this should be pretty fine. So now we can replace this LNA call size with size of the LNA3 call type. The compiler can calculate these sizes. We do not need to provide them manually. Now we can remove this procedure with the comment. Then we have this call get name. It is called name here, but we will call it callee. So let us just find the call get name, and instead of so we need to provide the correct type in here. This type is a pointer to the LNA3 call. And it will give us the ability to access its fields. To be honest, we can just say that the callee has this LNA3 variable expression. It isn't true for the final version of the language, but it is true for now because anything else cannot be cannot be parsed yet. And this should be fine. And now I actually wonder if we need this variable. Cannot we just write it this way? Oh, fantastic. It does really work. So, yeah. And then we can actually it is not very fine. Let us just replay this name usage. So we we make this shortcut so we do not write the whole expression each time. We assign this collie to the parsed expression, but instead of name, and I reassigned the parsed expression here, it was the problem. But this is definitely not true, because the thing that is in argument isn't a variable expression, it's just a generic, it is just a generic expression. Where do I use it? I just calculated the number of arguments. Well, then we do that the other way. We just replace this parsed expression with the collie field, and then we do not need this assignment anymore. Okay. Call get name isn't used anymore. We can remove it. Then we look for the call set name, and it is used here. Result has the type not recall. And the result should have the proper type then. Not restatement. It isn't true. It is not recall. So now we can just say that result collie is collie, and we can remove this call, and after that the arguments are parsed. So this procedure can go as well. We remove it, and now we only have the arguments. Call get argument. Here we use the parsed call. Argument count plus 1. That would mean that we take the arguments variable and access it at argument count plus 1, and we need to dereference the variable, this is fine. Then we have call get argument here once again. Okay. So we do actually the same, we just replace it with arguments at argument plus 1. Okay, so here's another place where it is used, in a type call. It is a type checker that isn't really implemented. So we set the parsing node to the arity call, and we say that we want to get its argument, current argument plus 1, and then go to what is actually this type binary expression. It takes a parsing node word. No, type binary expression. No, it takes the arity binary expression. So we can assign this type to this argument tree variable, and current argument that it is word. This is fine. Are there any other usages? It was call get, I think. So call get argument isn't used anymore. We can remove it, and then we only have this set argument. And this is the parser as expected. The result already has the correct type, and that means that we can just assign to the arguments at argument number the parsed expression. This is another usage, and it is the same place, and we just assign. This is the reason why we have 8 arguments and not 7, because to see which argument is the last one, we set last argument to nil. And therefore we need an additional 4 bytes for saving the nil after 7 arguments. Argument number is nil. Okay. That compiles, and that means that we can remove also this procedure, and then we got rid of all the set calculations for the calls. And now another thing is, of course, that instead of saving nil, I just want to know how many arguments are there. So let us add an additional variable count of type that. And actually in the parser we already had this thing. I do not know what was the function name. It was this parser call, and this argument number is actually the number of arguments. So we can say that result count is argument number. Now in the 3 address code, so arity call, the first thing that we do here, we calculate the number, the arguments. So I iterate through all the arguments and look for the nil and the array, and the count will be saved in this argument count variable. Where is the loop here? This is the loop. So I jump to this count, but I can just assign this argument count variable right away, and I say that it is parsed call count. Actually we do not need to compile it. Let us remove this code and then see whether it compiles. It does not. What is the argument count? It is probably off by 1 in one or the other direction. Yes. Now I only need to find out where the actual calculation is run. So here we begin with argument number 1. I think actually that here it is calculated wrong. So I begin with 1 because we handle the first argument, then we increment the argument number by 1. And for example, if I have the second argument that I handled, then I have 2 arguments, but argument number will be 3. That means that we need to assign -1 to it, and then we can remove this minus from here again. And we can move this statement in here and remove this code. this also means that I probably do not need, I think that I iterate the arguments. So after the three address code generation, we do not need the node from the abstract syntax tree. That means that after that I do not need this nil at the end of the argument array, but I think that it was used in the type checker. Elna type call was it probably, and here I iterate the arguments again, and I call the type checker on all the arguments. But we need to rewrite this thing a bit, and we actually want to compare whether the current argument is less or equal the parser node count. And then instead of assigning, so current argument, yeah, let us compile it once and see how it crashes. Oh, it doesn't crash. And I think that we do not need actually this argument tree. Let us just pass it in here, and then we actually have everything we need. So now I go back to the Elna tree call. No. How was the procedure called? Parsing call. Exactly. That was the name, and we do not need this nil anymore. So let us go back to the type declaration and definition for this Elna tree call. We can now say that it has 7 arguments, so that the type has the original layout of 44 bytes. When the parser parses the arguments, it doesn't know how many arguments does this function have, so it cannot locate an array at once for all arguments. Therefore, it would be nice to save the arguments in a list and not in an array. But the problem is that expressions are not lists. For example, statements have this next field and declarations as well, because also declarations are basically a list and statements are lists, but not the expressions, and doesn't make sense to add the next member because expressions are not always lists, but only in some places, like the argument list, for example. And I think that we do not have any generic list data structure. So these are, for example, instruction lists. Errors are also lists, but errors are a different kind of list where we have two references to the first and to the last element. Yeah, I'm not sure if I should create an expression list, so a list only for the expressions, or just but it will be actually a generic list, because it would contain an expression pointer and then a pointer to the next entry. So Elna, I already had help types, Elna tree conditional statements. These are, for example, help types that are actually lists, that are also lists with two elements, with the condition and the statements belonging to the condition. So L03 expression list would be the type name, and then we have an expression in here. It will be L03 binary expression, and the second thing is also next, which points to the next entry. So it is an entry of a list, and then the last entry will be nil. And when we have all the expressions in here, I haven't defined. So Elna error is basically probably an entry. So this is the list structure that will point to the first and last entry, and it is an entry itself. And actually Elna error looks pretty much as something that we could use. So I allocate it, set it to nil, and assign it as first and last element. and then we can save an entry there. I do not save any type here, but errors I could just extend them the same as I do with statements, because we will have different kinds of errors. Yeah, I go with this silent tree expression list. So we have defined it, and now we should define it before we use it. So, and now we can define a new member. We will call it arguments with an underscore for now, and we will assign it a pointer. Actually, it shouldn't be a pointer, it can also be the record directly, I think. So this is our parser, and let us see what we do here. So basically I parse the binary expression, and then I assign this binary expression. Let us initialize the new member being the result arguments. Let us set it to nil. We also will need a reference to the current list entry. We will need a reference to the current list entry. So here, this is the right parent. Oh, this is if the procedure does not have any arguments at all. And it is the loop, and we check here for a comma. Or where do I jump? I jump into this loop after argument parsing. And if it is not a comma, then it is a right parent, and so we just keep it. Okay, this is actually fine. So we pass, and here we know that we have to pass the argument. It actually means that we can allocate the memory for one list entry. I could just do a dynamic array. I have to allocate the memory anyway if I see any argument, but well, whatever. So we had this, what was it, argument entry, I think. We say that argument entry is a pointer so it is size of L03 by no expression list. So we allocated the memory for it, the payload inside of this thing. So I'm going to look at the definition of the type, expression list, and this expression list contains L03 binary expression. What is actually L03 expression? Do I use it somewhere? It is the base expression. Okay, I see. So we save an expression point in here. I actually cannot set it to nil because it is not a pointer. It is a record. But I can set the first field to nil, or I can just set this whole, or I can just make this whole thing a pointer. So expression list, it is used in here, and it is probably a pointer and not a record. So let us do it a pointer to the record, to the next entry, to the first entry of the arguments. So we set it here to nil, then we allocate the new one. After allocating the memory, we can assign expression, and we assign this parsed expression to it. Parsed expression, and we set the next element to nil. This is the new entry. We have we have also to keep track of the last entry. How can we do it? At this point, I can actually check whether the main call expression, so result arguments, whether it is nil. If this is the case, then Then we allocate the memory first. Then we allocate the memory first in the result arguments itself. So we assign result and please its underscore arguments. We assign memory to it. And we assign, or probably we still need to allocate the arguments entry, but we need to assign this arguments entry to the arguments entry itself. Arguments entry to the result arguments. If it is not the case, then it is not the first argument, which means that arguments entry points to the previous argument from the previous iteration, and that means that we can dereference it and assign the new memory to the next pointer. So we allocate it. This way we have assigned it to the last element of the list, and after that we can basically just say that arguments entry is arguments entry next. Something like this should probably work. Then I actually want to move it a bit around and assign result arguments to this variable. Then I reset the next pointer on the newly allocated entry, and that's it actually. Then I can save the expression there and go to the next loop. If we are looking at the last element of this list, then I just assign it and we leave the loop, and we have the number of arguments. This doesn't work as expected. Some semicolons I'm missing, and we still have problems. So here we take the size and the next. I actually do not use it yet, and it is just assigned and set, but isn't really used. So we can probably just remove a few things and see whether it compiles then. So in both cases we allocate memory. What would happen if I do not assign this arguments entry variable? It still breaks. Can it be that I have a typo somewhere? Yes, I do. Is it argument set entry or the argument entry? This is actually argument entry. So this can go and this can go. Okay, that's better. Now we have the same assignments duplicated one time, this 7-element array, and the other time in this list. And we use this argument list in two places: in the type checker, type call, and actually argument 3 isn't used anymore. Yeah, let it be expression list, and we assign argument 3, we assign the parser node arguments to it, and if argument 3 is not nil, then we take the expression from it. So argument 3 expression, and that's it, and we go to the next element. So we just say that argument 3 is argument 3 next, argument 3 next. That does what it should. Now we do not need the current argument counter. And the second function where it is used is the generation of the 3-address code. So we go to the TAC call, and this will be fun as well. So parsed expression is the current argument. For 1 it should be nil. I define a new variable and then just remove the unused ones after we do the switch. Let us call it expression list or expression entry or argument entry. Argument entry was the name. Let us call it argument entry. It will be an L03 expression list. And we will assign it outside of the loop. For example, here we will say that L03 no, that argument list argument entry is parsed call arguments, and then we check if it is nil, then we go to the finalize label, which doesn't do anything interesting. If it isn't null, Then we need to assign, so I do not do any jumps here, and where we increment the argument count, we want to say set the argument entry to the next argument entry. Next, and see if it crashes the compiler, and it does not, as it seems. And now we only need to take the things not from this parsed expression, but from the argument entry expression. And it is actually the only place where it is used, as it seems. So we can replace it. And now we do not need this stuff anymore. Okay. I still check whether the parsed expression is nil. Why that? I actually need to check whether the argument entry is nil. And this finalized label is actually just after the if statement. That means that we do not need this jump at all. Is the label, and the label isn't used anywhere else. We just can negate this condition and then get rid of the label. What else? So we were removing this parsed expression thing. Exactly. We do not need to assign it anymore. What about this argument count? It isn't used anywhere else. Actually, we also want to remove the variable itself because it isn't used either. So we can get rid of it, or I probably can use it the same way it was used before. So we let the variable in here for now, but what was it? Argument count isn't used anymore. So we can remove this one. Oh, it is used here. I just reuse it after that. But we actually do not need the variable here. We can just use the field access directly and get rid of this thing. And it doesn't compile. Why that? Okay. Parsed call count, parsed call collie, parse call arguments. Argument count. Oh, here it is used. I see. But now it should compile. And it does. Of course. So we can remove the variable itself. And as I said, this parsed expression isn't used anymore, but we actually want to use it. We assign this curly pointer to it, and then instead of using name, we can use parsed expression name and parsed expression length. I really should have renamed this variable, but yeah. So whether it compiles, it looks fine. Then we can remove these two variables and from the list as well. Parsed expression is used now. Then this operand. So this pseudo register is where the return value is saved, and here we have our dynamic array and the iteration. Everything else does actually look fine, I think. So well, the lines is a bit too long. I mean, what is the problem? We can just write it in 2 lines, and that's it. So parsed expression is used. Instruction, first instruction, current instruction, and call instruction. So first instruction, call instruction is used in here. Then we have instruction, then we have first instruction, current instruction, and that's it actually. So all these instruction variables are used. Then we have argument type, value, and length. They are used as well. Arguments operand is the array, I think, yes. And then we have this argument entry variable that is used as well. Let us do the final. Oh no, not the final compilation. We still need to remove the old field. So we go to this ELNA 3 expression list. No, not the expression list. The call. And actually we do not need these arguments anymore. So we need to remove the assignment in the parser. Argument number is needed to set the count at the end, so it will remain as it is. I do not need this parsed expression variable. So let us check if that compiles without the arguments in the array. It does. And we do not need this parsed expression. We can just assign the result of the procedure to the theme directly. And parse expression isn't used anymore. So we can remove this variable token kind, argument entry. The other things actually look fine. And we can remove here the new line. And well, call end is used in here. Okay. Yeah. And then the second try, we remove the field and it already looks better. So it compiles, and the one thing that I want to do is actually to rename this underscore variable without the underscore. So we remove this underscore and look for the arguments variable with an underscore and replace it and here as well, and probably also here. Yeah, and we compile it. Now I exit the editor. So I simplified the call statements and expressions a lot, how they are handled in the parser and in the 3-address code generation pass. And also we fixed this limitation that procedure call can have at most 7 arguments, at least in the parser. It still needs to be fixed in the code generation pass, because all the arguments are saved currently in the registers, and our target architecture, that is RISC-V 32, has only 8 registers for the arguments, and other arguments have to be saved on the stack. So it still needs to be implemented, but at least this limitation is lifted from the parser, and we will continue our work next time then.